So far we have seen everything. So now it's time for us to decide how to use these results. We have all the results that we want. We have different kinds of results. Now it is in our hand to use this all the equations properly at the right places. There is a section that I would like you to read. I'm leaving it as a self study, leaving it for self study. It's orbits for the two bodies. It's very easy, and I have described it in the notes, and it is particularly easy for you to understand. I have written in a way that it is for self study, so you won't need any external explanation. It's self explanatory. So finally, we are at the end of our topic, central force motion. Just give a big round of applause for yourself. You made it this far. I'm really happy for you guys. So let's start with Kepler's law. There are three laws of Kepler's that in the start of the lecture, in the very beginning, I started with Kepler's law, so that I just stated the statement, and we found that we don't have necessary mathematical development or necessary physical understanding to describe all the three laws in terms of equations, so to speak. So if you remember this, I hope you do have my notes. So this is that section. This is the particular section that I started with. Then we moved on to the planetary orbits and described what's called as a reduced mass system, derived the force law, and all the things. But now we are in a place to start with the Kepler's law. So let's start with Kepler's law. Okay. Johannes Kepler, great man. So, starting with Kepler's law. So, first law is the elliptic orbit law. What does the first law say? Each planet moves in an ellipse with Sun at one of the focus. It's particularly kind of it specially says Sun at the focus, but it can be extended to Sun-like object. Alright, so that's one of the key things that you need to note here. So if you know that each planet moves in an ellipse with Sun at one of the focus. Let me write it down though. Each planet moves in an ellipse with Sun at one focus. So when this elliptic condition arises, so if you say when the energy, okay, I need to describe in terms of, and I'm going to talk about this orbit. I'm going to describe this in terms of two important things, which is energy and epsilon. That's what we want, because all our equation can be broken down into these two particular quantities, and angular momentum, of course, can be written in all the states, but we currently are not interested in that. So if you remember, I mentioned what happens when so when energy, so to speak, is between the two boundaries. So I'm just trying to formulate the graph. Okay, yeah, I got it. Right, this. So when the condition of elliptical orbit arises, it's when the graph here shows this. This is the region where the elliptical condition arises. For that, I need to have my energy minimum. So let me state, when energy minimum is greater than 0, not the E, but the energy minimum as a whole. So I can formulate my epsilon to be equal to 1 plus 2 times E L square upon mu G m1 m2 r square. This is nothing but one of the fanciest definition of epsilon that we used so far in our course. So again, yeah, I mean, there is no laws of generality if you use this too, but we are not going to discuss hyperbolic orbit, so yeah, let's keep it this way. It doesn't matter. So epsilon must lie between. So epsilon must lie between these two ranges. Why? We again need to go to the graph. You see, why epsilon needs to lie between these two. If you see, there are two turning points, one corresponding to R minimum and another corresponding to R maximum. So this, it creates a boundary. Similarly, this epsilon condition is nothing but a boundary that and you see, it's not less than, or it's not just less than, it's less than or equal to. That means you can have epsilon I'm sorry, there was a video cut between the two because my phone ran out of storage because I made videos like that. Today I made a videos that were almost 40 GBs, so I had to delete all of them. I already uploaded all of them to YouTube, so I don't need this video anymore. So one of the reasons that we need this boundary is because that it's less than or equal to, not just less than. So it characterizes R minimum and R maximum as we know it exists. Now, so this is clearly the E must lie in this range. Now the orbits are either circles or ellipses. That's fairly easy to see. The orbits are either ellipses or they are either circles. But remember this fact. This is a fact. I want you to remember. The ellipse only when one central force, remember, one central force is acting. Really sorry for my handwriting, but that's the best I can do in the situation. Now, so this is my ellipse. So when this ellipse arises, it's ellipse only when the the central force is acting. Only one central force is acting. Now, the gravitational force due to all the other bodies are negligible when we consider this effect. I have told you in the very introduction of the lecture that when I take two bodies, say I'm taking this as sun and this as earth, there are millions of planetary bodies between them, or millions of bodies in the sense that you have what's called as the celestial dust and all those. But my concern when using between these two laws is just using sun and earth. That's all exists. That all exists to my view, that all exists to my formulas. I don't care that exists Mercury between them, that exists Venus between them. I don't care a damn about it. So that's the first law. That's all about the first law. The second law states that the radius vector from the sun to a planet sweeps out equal areas in equal intervals of time. Now, if you remember the animation that I showed you in my computer, it states that it revolves in an elliptical orbit, but when it's closest to the sun, it moves faster. I mean, the radius vector from the sun to a planet, it sweeps out equal areas. Okay, let me try to draw it. I don't know if I can draw. Now you get the image. I know. So rather than making you confused by my drawing, just keep it intact. So let's start with the second law. It's the law of equal area law. The radius vector from the sun sweeps out equal areas in equal intervals of time. So let me show you a magnifying image of what I mean by that. Sweeps out this equal area, this particular fashion, and this is my theta, this is r, so this is theta and this is nothing but by using the arc length formula, this will be my r delta theta, right? Because this is my delta r. Now, as required by the formula, the area is equal to this triangle half length, this is length, right? Length to height. Alright, you're getting it, right? Let me tell you what I've done. See, this is the small angle that it takes, and this is my r. Now, then this distance from here to here will be the length, this length times this, which is r delta theta. Now I define another cross-sectional delta r. If I construct this line, and this is my arc that has been taken in the ellipse, in the elliptical orbit, that meant the sweeping. In this case, I can define my delta A, not just A, but a delta A as half r delta theta height into this particular length for this particular triangle plus half, now r d theta height into length of this triangle. There are two triangles. You see, there are two triangles, delta r. Alright, don't confuse yourself. There are two triangles. For first triangle, this is the equation, and for the second triangle, this is the equation. r d theta is same for both the triangles. Alright, don't confuse yourself. It's very easy to get carried away. Now I have what I can do is I can integrate this by by time. I get differentiate by time, theta delta a r. So if you want, you can just say that I just multiply throughout by 1 upon delta t, delta t, r theta delta t. This is delta theta. Now I will use the limiting condition where I state my delta t tends to 0. Then what would happen? This is nothing but dA by dt. Then I will have half r square d theta by dr, because this r dr, this term vanishes. We know, alright, we know that the angular momentum is related to angular velocity. You remember I told you this is one of the most important formula. by this particular equation, right? The angular momentum is related to d theta by dt. Thus we can use L upon 2 mu. You see, now you see L is constant. It's one of the constants of motion. Mu is mass. Alright, it's mass. It is also constant. 2, it's a number. It is all a constant. That means this particular term is also a constant for me. So derivative of a constant implies my a, the rate of change, that is the rate of change of area with respect to particular time is constant. Alright, my a is the rate of change of area, dA by dt. My a is area and dt, that means the rate of change of area with respect to time is constant. You see the role played by this equation d theta by dt. It's amazing. That's about the second law. Let's start with the third law. Now, in the third law, I want to emphasize the, I don't know if you understood the elliptical orbits. If not, just go and just see the results, because we're going to use it. I'm not going to use the whole elliptical result, but just the few parts of it, like a touch, a pinch of it. So what does the third law imply? The third law states that the period of revolution, capital T, of a planet about the sun is related to the semi-major axis, which we define as A, of the ellipse, is equal to T square is equal to K A square A cube, where K is same for all the planets, it's a constant. Now, the third law is called as the period law. Alright. Okay, my handwriting sucks. Now, I stated law, I'm not going to state it again. I'm going to use the second law. Alright, from second law, I have dA by dt is equal to L upon 2 mu. I'll take this 2 mu to this LHS. I get L. Now I just take this dt. Now I'm going to integrate this equation dt, and the limit is from 0 to t for time. I cannot leave this as indefinite integral. It will leave me a constant, and again it's not worth it. Secondly, now dA will depend upon what orbit I choose to emphasize, so I'll just write orbit. So for our case, the orbit is an ellipse, so the area ellipse orbit is dA, which is equal to pi times AB. Let me tell you how I got this. Diagrammatically, okay. This is an ellipse. Distance from here to here is my A, and similarly, the distance from here to here, not this, from here to here is my B. Thus, pi times this AB, the product AB, will give me the area of my ellipse. So, I integrate it to mu pi AB L T. That means I have T is equal to 2 mu pi AB upon L. But I cannot do anything with this because my L is in denominator. Whenever something is in denominator and it is just a single power, you need to know that it's useless. I don't know how, I don't really know how physically it is true or how mathematically it's true, but as far as I have seen, I have encountered my physics journey, I have seen whenever something is in denominator and it is important, like constant of motion, and it is a single power, it's useless. But again, I cannot do anything with this equation. I'll try to square it, and even if this is not true, just my observation, even this is not true, let's say I'll square it. Why? Because I don't know any equation. If I substitute L for that matter, I'll just get something which I got, which I just use it. I'll just get, which I just use it. So I'm using the equation which I derived, again using the same equation to derive something else, which is absolutely preposterous. So I'll square it. I'll get 4 pi square mu square a square b square upon L square. So my L square mu square, okay, 4 pi square mu square a square b square, and my L now can be written in terms of this constants. If you remember this, I hope you do, because we just did a couple of lectures back. So now I have everything in terms of, I have pi, I have mu, a and b can be determined by graphically. Mu is another constant, g, m, 2 constant, a can be determined, and my epsilon is again a geometric quantity which can be eccentricity, which can be determined for the particular kind of ellipse. Thus, by simplifying again, 4 pi square mu square a cube upon mu g m1 m2. Thus, for in cases of reduced masses, which is the case, reduced mass, my t square is equal to 4 pi square a cube upon g m1 plus m2. All the emphasis is the t square is directly proportional to a cube. That's what it matters at the end of the day. So finally, we are done with the everything. So let's go to this every describing central force motion. So I hope you understand I taught you. If not, just tell me, I just try to do it better next time. So any doubt, do feel free to ask me. Thank you.